This week's lab is known as spot testing for some common anions. We know that anions are negative ions. So these are all last names, chloride, fluoride, sulfide, so forth, that these are negative ions that we are going to qualitatively test to see if the presence of them are existing in our solutions. So let's begin with just a brief discussion about two vocabulary terms that we've been really using all semester long, and let's just reflect upon that. We have two types of terms, quantitative versus qualitative, and we have indeed done both types of experiments. Quantitative analysis deals with the determination of the amounts of certain species present in the sample, the amounts. So based on very careful measurements, quantities, see that word in there, quantities or amounts, very careful measurements using mass data, volume data, and so forth, we're determining a specific amount of a certain sample. For instance, we had a week where we were determining between sodium bicarbonate, potassium bicarbonate, or we had the compounds sodium carbonate, Na2CO3, versus potassium carbonate, K2CO3. This had a title in the experiment called mass percentages. In those mass percentages, we used very careful measurements to determine the identity of the sample. This was a quantitative analysis. Tell me the identity of the unknown by using very careful measurements. On the flip side of that are qualitative measurements. Qualitative measurements really has the purpose of trying to decide if the sample contains the unknown that we're testing for. If the sample contains the unknown, and I'll just put that as the ion, or not. Is it there or not? Not how much of it is there, just if it's there. So, measurements just aren't as important here. For instance, in a moment when we go into specific directions, I noticed that the lab very carefully tells you to measure 1 ml of a, let's just say, 6 molar acid solution. It is not critical that you measure precisely 1 ml. Measurements in terms of quantities are not critical. I'm going to let you know somewhere between 5 to 6 or even 7 drops using a dropper pipette, one of our plastic pipettes, are plenty. I mean, just enough so that you can see the sample. Measurements are not critical in qualitative analysis. It's all about observation. Do you see a positive test or not? Quantitative, it's all about accurate measurements. Very careful, use that analytical balance and tell me precisely how much of the sample is there. With qualitative, the measurements aren't as critical, and it's all about the power of observation. This week, our lab is qualitative. We are going to be testing some unknown anions. To see a positive test, we run it on a known, and we compare it to the unknown that we are given. Are they behaving the same, or are they behaving differently? Well, let's talk about those very ions that we'll be testing. There are 6 of them in our lab this week. Notice that the list that I'm providing you is different than that found in our lab manual. The lab manual begins for this week's experiment on page 19. We have some adjustments to make in our list. In this experiment, we are spot testing or analyzing a mixture that may contain any of the following. First one, carbonate, CO3 minus 2. Notice these are all negative ions. These are all anions, a negative ion, anions. Carbonate, sulfate, chloride, acetate, thiocyanate, and ammonium, a positive. So he's the rebel, isn't it? So this truly is what we call a cation, a positive ion. All of the first 5, of course, were anions. So testing for ions. Notice we're eliminating phosphate, PO4 minus 3, cross it off. PO4 minus 3, we're not testing. Sulfite, SO3 minus 2, we are not testing, cross it off. And then the nitrate, NO3 negative 1, we are not testing, cross it off. But we're adding the ammonium ion, please add that to your list, NH4 plus 1. So let's take a moment and adjust our report page. Please turn your lab manual to page 23. On page 23, this is the observation and report sheet. Notice that it's a column format. The ions are listed down in the first column. Carbonate, then sulfate, then I notice phosphate, PO4 minus 3, cross it off. PO4 minus 3 is being eliminated, cross it off. Right underneath that, sulfite, SO3 minus 2, it's being eliminated, cross it off. We're keeping chloride, we're keeping acetate, we're keeping thiocyanate. And the very bottom line reads nitrate, NO3 negative 1. I do want you to cross that off, but in its place, let's add the ammonium ion, and we'll record our observations on that very last line. I'm going to do it that way because it will be the last ion that we test in the procedure, so it will still be sequential. The other thing you'll need to do on this report page, once you're given an unknown, be sure that you identify it by the number, and ultimately what we're trying to do is to test for the presence of those ions in our solution. So we have 6 that we're testing: carbonate, sulfate, chloride, acetate, thiocyanate, and ammonium. Make sure that you've got 6 rows ready to go on your report page for page 23. So that's 6 of them. Notice each of the tests, as we're staring at page 23, each of these tests are actually being performed 3 times. Alrighty, so as we're following the directions for each one of these testing ions, the procedure is done to 3 separate solutions. One of them is the stock solution. I call that the stock solution. It's just fresh out of the jar right from the chemical tray. So you'll take out a stock solution and perform the test. Then you're told to dilute the sample. So using a graduated cylinder, a 10 ml graduated cylinder right out of your drawer, I want you to place 1 milliliter, and be as accurate as you can in this particular measurement. Alrighty, I want you to measure out 1 ml of your sample, and I want you to add 9 mils of water so that at the end you have a 10 ml mark. You've diluted to a 9-to-1 ratio, resulting in 10 mils of a new solution. And here's the reason we're doing that. I know I can see a stock solution that's very concentrated, and I get a great feel for what the presence of the ion is testing positive as. Do I see a precipitate? Do I see some bubbling? Is there a color change? What might indicate the positive presence of the ion? But see, my unknown might not be as concentrated as that stock solution, so I'd also like to compare that behavior to a diluted sample. Maybe the precipitate is there, but instead of really thick and chunky, it's more cloudy. Maybe instead of rapid bubbling, there's a little bubbling. I want to compare concentrated versus dilute. So I have both observations under my belt to determine if my unknown is indeed doing the same. Is my unknown reacting in the same way as the concentrated or dilute solution of the known? If it is, the ion is there. And if it's not, the ion is absent. So we're going to record observations for each. A concentrated, that's in the next column after the identity of the ion. It says stock solution, that's the concentrated version. Then the 9-to-1 dilution, that's the diluted solution. 1 ml of the stock, add 9 mils of water. Be sure to stir it up. And then the unknown, how is it behaving? Observations for our data table. Describe what you see, describe what you smell, that sort of thing. Now, some of these might need a water bath. So as you're beginning, one of the first things I recommend doing is find yourself about a 150 ml beaker from your stock drawer, turn on a hot plate, and just put that half full of water in a small beaker, 150 to 250, doesn't matter, and just get it to a gentle boil. You may, and it depends on what you find in your sample, you may need a water bath, so you might as well get it going right at the start. Just get it going and ignore it. Of course, don't let it boil dry. Keep adding water if you think it's going too low. Alrighty. So ultimately, our purpose, tell me the identity of the ions that are present in your unknown solution. Now, great recommendation after you perform each test, carbonate, then sulfate, then chloride, and so forth, just take a moment and clean your glassware between each test. I want you to clean out your grad cylinder. We don't want to have any possible source of contamination. Clean out the beakers that you're using your test tubes for. Alrighty? So make sure that you're cleaning your glassware before you go to the next step. Now, here's what I recommend as we proceed. I'm going to put on the next slide, but I'm going to tell you something very important. What I'm about to do is the advanced study assignment. I am altering what the text has here. Page 25 and 26. The reason I have to alter is because this is written for all of the ions, and we're not testing all of those ions. So as I was reading through this, the advanced study assignment made no sense to assign you because you needed to see or needed to read about all of the ions present. Based on what I have in stock in the lab, I had to eliminate some of those ions and add another one. So page 25 and 26, we're not even going to look at those pages. Cross them off of your to-do list. Instead, take out a separate sheet of paper, a notebook sheet. Pause the video if you need to and go get a separate sheet of notebook paper and start back up. Because what I'm about to do, step by step, I'm collecting as your advanced study, not page 25 and 26, but what I'm about to do with you for each one of these tests. Alright, so now you have a paper out. Let's begin with the first procedure, testing for the carbonate. And notice this is on the bottom of page 19 is where this begins. Add 1 ml of 6 molar hydrochloric acid to 1 ml of 1 molar sodium carbonate. This is the test for the presence of the carbonate ion. Now remember what I'm suggesting. The 1 milliliter is not important. Take anywhere from 5 to 7 drops from a dropper pipette, a little plastic pipette. So you'll be walking up to the chemical cart with a plastic pipette. Take out a sample by drawing up the acid and just flip that pipette over as you walk it back to your desk. Leave the stock bottle on the cart. Take a sample of it in a pipette back to your desk. The 1 ml of sodium carbonate is the other reactant. Again, 5 to 7 drops. Use a test tube for this particular reaction. Into a small test tube, place some acid in with some sodium carbonate. Quantity is not critical. Alrighty. So let's think about the chemist. Now remember, I'm just going to pause and remind us of the procedure. I'm doing this 3 times, so I actually have 3 tubes out for this particular test. 3 tubes. Into tube number 1, I have straight stock solution. Alrighty, straight stock solution in my test tube. So I'm putting in 5 to 7 drops. And what I'm putting in there is 1 ml of acid with 1 molar sodium carbonate, and I'm mixing them up to observe. Into a separate test tube. This is my diluted stock solution. My diluted stock solution is this. We're testing for the carbonate. So before I can even begin this, I've got to dilute down with that 1:9 ratio. I place in 1 ml of the sodium carbonate. And into the grad cylinder, I'm adding 9 more mils of water. And please stir so that your sample isn't down here. Because if I take my pipette and just draw off a mil or so, I'm only going to get water. We want a uniform solution, so stir it. Take a stirring rod and make sure that you're agitating that for a complete homogeneous mixture. From this new experiment, this new little solution here, that's what I'm going to put in a little bit of diluted sodium carbonate and add the 6 molar HCl to that. So stock solution plus acid, diluted solution plus acid, and then in the third test tube you have your unknown plus acid. Alrighty, so 3 separate times we're running the same experiment. Let's take a peek at the chemistry, and this is what I'm after. You're going to write the chemical reactions with me and just talk about what would we expect to see if these occurred. So the first category here is going to be called a molecular equation. In the molecular equation for the carbonate, label this on your paper. This is the carbonate test, the molecular equation. The reactant of HCl, aqueous, with the reactant of sodium carbonate, aqueous. Think about the pattern of chemical change. Here we know hydrogen chloride in water is hydrochloric acid. It's a +1 -1. Here we have sodium carbonate. It's a +1 -2 for ions. Outers, inners, the double replacement pattern. Hydrogen goes to carbonate, sodium goes to chloride. And when we predict products, we do so based on charge. If H goes to carbonate, H is a +1, carbonate is a -2, we have to crisscross and we get H2CO3, carbonic acid. We'll revisit that product in just a moment. Sodium chloride, based on charge, Na+, Cl negative. Na+, Cl negative. Now what do we expect here? Let's see, 2 sodiums, 2 sodiums, 2 Nas, 2 H's. You have to double here. A 2, 1, 1, 2 balances this equation. This was the double replacement part of our equation. Double replacement. Sorry, that's messy. But what do we know about this carbonic acid? As soon as it forms, we know that it's unstable. And as soon as it forms, it breaks apart, doesn't it? We have the double displacement, but it is going to follow the pattern of a decomposition. You're going to see carbon dioxide and water from the decomposition of that initial product, H2CO3. Carbon dioxide, water, and sodium chloride are our 3 products in our molecular equation. So what about the driving force? See this right here? You will definitely see bubbling occur. If carbonate is present, carbonated beverages, they bubble, don't they? Here is the driving force of this double replacement reaction. So the presence of carbonate can be detected by bubbles of CO2 being released. Let's turn this into a complete ionic equation. Break apart only the strong, correct? So breaking apart anything that is a strong electrolyte. HCl, it is one of the 7 strong, so we need to break that apart. 2 hydrogen ions and 2 chloride ions. When HCl separates, as strong electrolytes do, they dissociate into their ions. We get 2 groups of hydrogen ion and 2 groups of chloride ion. Sodium carbonate is indeed a soluble salt as well. It will dissociate. See how we're going to get 2 sodiums? We come up with 2 Na positive ions, and there's just 1 group of carbonate, CO3, 2 negative, the charge on the carbonate. And we see the arrow. Carbon dioxide and water are both molecules. They do not dissociate simply because they're not built of ions. Leave them together. And how about the sodium chloride? Well, we know that that is a soluble salt as well. So when we write out sodium chloride, we get 2 groups of Na+ and 2 groups of Cl negative. The complete ionic equation takes the molecular and simply dissociates it. Let's examine for the presence of spectators. What ions remain unchanged from the left to the right? I'm noticing chloride. Circle it with me on your paper. chloride is called a spectator. It's the same as the left to the right side of our arrow. And now I'm spotting also the sodium. Na plus is a spectator ion. When we move from the complete ionic to the net ionic, we're eliminating the spectators and writing out the chemistry. What's left if we eliminate the spectators we've circled above? I would see 2 aqueous hydrogen ions reacting with 1 aqueous carbonate ion, forming carbon dioxide, water. The driving force are the bubbles of CO2. So friends, if indeed your sample of unknown contains the carbonate ion, the evidence you will be seeing, or evidence you're looking for, is the bubbling of CO2. We've written a molecular, a complete, and a net ionic equation for the test of carbonate. Let's take a peek at the next, the sulfate. Sulfate is a polyatomic ion from our chart carrying a -2 charge, sulfate. Now remember, as I proceeded from my carbonate test that we just finished, I'm taking a moment and I'm washing all of my glassware because I don't want any chance of contamination. Wash up and then continue when ready. Now again, we're going to walk up to the chemical tray and we're going to take dropper pipettes, draw up the molar acid and draw up the sodium sulfate and barium chloride. So this actually has 3 samples to go collect with your dropper pipettes. Draw up plenty of them and just bring them back upside down to your table and perform the chemistry at your desk. Alrighty. So let's figure out what's going on. We're going to take hydrochloric acid as my first reactant, and I'm going to add that to sodium sulfate, Na2SO4. Alrighty, my first set of experiment here, HCl reacting with sodium sulfate. Notice again, the 1 ml isn't important. Just from your dropper, anywhere from 5 to 7 drops. We're not caring about quantity, we're looking for observation. So same thing, just some acid with some sodium sulfate. This is your stock solution. We're testing for the sulfate ion. Alrighty, so what do we have so far down here? Into a small test tube, I take a squirt of HCl and add it to a squirt of sodium sulfate. Pattern of change, H goes to SO4, and based on charge, I still like to help students learn we're always connecting by charge. So sometimes if I just take a moment and write those up there, it helps me when I crisscross and predict products over here. So when I write H hooked to sulfate, I know based on charge, it's a +1 -2, so we get H2SO4. And when sodium goes to chloride, we get NaCl. And based on charge, there's just 1 ion of each, a +1 to a -1. Let's balance. 2 Nas on the left, 2 Nas on the right, 2 H's, 2 H's. 2 Cl's, 2 Cl's. There we go. A 2, 1, 1, 2 balances that equation. Alrighty. Now, if I think about the spectators, this is the sample that we're actually still testing for, isn't it? This is where the sulfate now lies. So let's take a look here, and I'm really just combining both of these into one set called molecular equations. Step 1, we turn the sodium sulfate into hydrogen sulfate. That becomes the very next reactant as we add the next ingredient. So I add 6 molar HCl to sodium sulfate. Stir it up, and this is what happened so far. The next step of direction says now add some barium chloride. So what's happening in the next step is the very product we made in the first step becomes the reactant in the second step. And that happens when we take BaCl2 and add it as a third ingredient into the same test tube. Now what happens? H goes to Cl and barium goes to sulfate. Hydrogen chloride, barium sulfate. So here we have HCl and BaSO4. Remember, based on charge, a plus with a negative, plus 2 with a minus 2. Here's our electrically neutral compounds, and I balance with a 2. Now notice what's happened. Step 1, we added acid to the salt and made a new acid. That became the reactant as we added barium chloride. What did we generate back? Do you notice how the initial reactant ended up to be our final product in the second equation? So they're going to simplify, aren't they? And if you notice here, I made hydrogen sulfate and then used hydrogen sulfate. There's some words for these. Write them with me. Something that is added to the reaction in step 1 and that is given back to you as the same ingredient in the last step is known as a catalyst. Something that I add to the equation to speed it up, to help it go to completion without itself being part of the chemistry. HCl was started with and ended with. It cancels in our equation. Here's a word for something that's made and then completely used in the next step. It's called an intermediate. In step number 1, we made sulfuric acid. In step number 2, we immediately consumed it. It also cancels from the overall equation. And what's left for our molecular equation? We had 3 ingredients we mixed together. The initial acid with the initial salt, stirred it up, and then added a third ingredient. Ultimately, this is the molecular equation. Sodium sulfate, Na2SO4, the ingredient left on this side of the arrow, reacted with barium chloride, BaCl2, the ingredient left on this side of the equation in the second. What's left over here? We see 2 units of NaCl and 1 unit of barium sulfate. It was a 2-step process to produce the barium sulfate. And this is what you're looking at as your driving force. You should expect to see the insoluble product called a precipitate of barium sulfate, BaSO4. It took 2 steps to get there, but initially this is our equation. So what do we see in terms of a complete ionic equation? Break apart the strong. Sodium sulfate is an aqueous salt. We dissociate and separate it into its ions. 2 aqueous sodium ions and 1 aqueous sulfate ion. Again, from the solubility table, we see that barium chloride is also an aqueous salt. It dissociates into its ions. 1 unit of positive 2 barium ion and 2 units of negative 1 chloride ion. Sodium chloride is also an aqueous salt. 2 groups of Na plus and 2 groups of Cl negative, carrying that coefficient and separating the ions. But right here, from our solubility table, we know that barium sulfate, check your solubility table with me and you'll verify it's insoluble. There's the driving force. The BaSO4 coming out instead of aqueous is now a solid. There's your driving force. That's a white-colored precipitate. What spectators do you see? Circle them with me. I notice sodium appears unchanged from the left to the right, and I see chloride unchanged from the left to the right. Those are known as spectators. We eliminate them when we write out our net ionic equation. Just by convention, we always write the positive first. You'll see the barium with its +2 combining with the sulfate with its -2, forming the white solid of barium sulfate. This white solid indicates the presence of sulfate. If it's not precipitating, the sulfate is absent. If there is the formation of a precipitate, the sulfate is present. Our third ion is thiocyanate. Thiocyanate. We don't use this one too often. He's a lovely polyatomic. It's just not on our particular chart. Thio is sulfur. Cyanate, Cn. Overall, it carries -1 charge. Alrighty. So clean your glassware. Before you move on to this test, take a moment and clean the glassware. And now we're ready to go on and test for the presence of thiocyanate. We're going to take a little bit of acetic acid. HC2H3O2 is called acetic acid. And potassium thiocyanate. And we're going to stir that. So this is like a previous slide where we had 3 ingredients. So we have 2 separate reactions to consider. First, we take some acetic acid, HC2H3O2. And again, just go to the chemical tray, draw up with a dropper pipette the acetic acid and carry it back to your desk. Same thing with potassium thiocyanate. Draw some up, bring it back to your desk. Same thing with iron 3 nitrate. Draw it up, bring it back to your desk. So this requires 3 separate pipettes. And this here is your stock solution because this has the presence of thiocyanate. This is what you'll take to mix the 1:9 ratio. I need the dilution step. So here we have acetic acid reacting with KSCN, potassium thiocyanate. And again, potassium's a +1, thiocyanate is a -1. Hydrogen is a +1, acetate is a -1. So when we take our 2 positives and exchange their places, we form HSCN, hydrogen thiocyanate, and again, based on charge, it comes out electrically neutral. And when potassium goes to acetate, we generate a new salt called potassium acetate. And again, based on charge, +1, -1, we have a balanced equation, all coefficients of 1. Then what do we add after we mix these 2 things together? Take the acetic acid, add potassium thiocyanate, stir to create a uniform solution. And next we're going to take iron 3 nitrate. So again, we're testing for the presence of thiocyanate. So now this ingredient becomes the very reactant we're going to consume in the next equation. Oh, that was supposed to be an S. Here we have HSCN, hydrogen thiocyanate, now reacting with, notice there was a subscript missing in your lab manual. There's no 3 right here, but it's iron 3 nitrate. So iron, parenthesis, NO3, taken 3 times. Hydrogen +1, thiocyanate -1. Irons +3, nitrate -1. Now what do we make? Well, hydrogen goes to nitrate, HNO3, and the iron will go to thiocyanate. The iron is a +3. The thiocyanate is SCN -1. So we get Fe SCN negative taken 3 times. Alrighty. And this is the true chemistry happening to test for the presence of the thiocyanate. This is going to give me a complex that is deep, deep red in color, almost like a blood red color. real deep red, maybe even brownish tint to it. Alrighty. So this right here indicates the presence of the thiocyanate. Let me just take a moment and get that balance before I walk away and forget. 3 H's, 3 H's, 3 nitrates, 1 iron. I think that did it. A 3-1, 1-3. So this right here becomes the chemistry for the presence of thiocyanate. First step is necessary to put a hydrogen on the ion we're testing so that when we add the iron, we can pull that hydrogen off and find that thiocyanate group. Alrighty. So a two-step molecular equation, 3 ingredients. But I'm not seeing anything that initially starts and ends. What I do see is one intermediate. HCN is produced and HCN is used. Alrighty. So this very first equation produces something that we then go on to use in the next step. Alrighty. But I'm going to just leave that and focus on this as we go on to the next particular step. Just a minute, Daisy. Sorry, friends, my dog wants out. Let's take this apart. A complete ionic equation. HCN, it's an acid, but it's not one of our 7 strong acids. We leave it together. Leave it together, and what do we get? I'm going to make sure it's balanced. Whoops. 3 HCN plus, this breaks apart, it's a nitrate. Nitrates are always soluble, so I get Fe plus 3 and 3 groups of nitrate carrying a -1. Alrighty. So Fe is a plus 3, broke one apart. 3 groups of nitrate, each at a -1. Over on this side, HNO3 is strong. It's one of the 7 strong we had to memorize. So it breaks apart. We get 3 groups of the hydrogen ion and 3 groups of nitrate ion. This is a precipitate. It's the deep red, dark colored solution that you've produced. It stays together. FeSCN taken 3 times comes out as a very fine, solid precipitate. The size of the particle that you're producing here is so small, it's very undetectable unless you were to spin it in a centrifuge, but the color is what will be unique for this presence. Alrighty. So what's our spectator? I just see nitrate. Go ahead and circle that. Go ahead and circle that, and we'll now know that it's a spectator. And what's left for our net ionic equation? We have 3 units of the weak acid, hydrogen thiocyanate, HCN. We have an ion of iron with a +3 charge. We have an ion of H+, 3 of them. And we have the solid precipitate, Fe parentheses SCN, taken 3 times. Here is the blood red color that will be a positive test for the presence of thiocyanate. I'm going to pause the video here, give you time to rest. We'll come back in just a moment. I'm going to go let my dog out.